until he's preparing, I'm going to resume the lecture. Today's discussion is mainly concept. Just discussion concept. Okay? So you have to understand concept. It's a very simple, but you have to understand that very clearly. Okay? First of all, I try to explain independence. Independence of vectors. Okay? So we have to familiar with this concept. Okay? Let's say vector is V1 to V, let's say N. I say those are independent or dependent, right? Kim Sang-woo, can you give your opinion what it means by those vectors are independent? So one thing is all these vectors, right? You can combine linearly. It means you can combine C1, V1, C2, V2, Cn, Vn. When you combine them, these are also vectors, right? These are also vectors, right? Okay? When you combine them, sometimes you can make zero vectors, right? You combine all of them properly, it may become zeros, right? So this is zero in case when all Ci is zero, it's obviously this equation holds true, right? 0 times V1, 0 times V2, then it's zero, right? Okay? This equation zero only if then we say these are independent. Okay? This linear combination of vectors becomes zero only if all coefficients are zero. Okay? Then let's think about it this way. Let me give an example. Let's say this R2. Okay? So I'll just give vector is 1, 0. 0, 1. Are they independent? How about 1, 1? Are they independent? Okay. When I have 3, are they independent? Why? Speak up. Or you can simply say, okay, space of R2, there are only 2 independent vectors available because they're 2-dimensional. Let's say when you have Rn dimensional, at the most n independent vector combination vectors, okay? There's no way to have 3 independent vectors in R2. Then another one is, how about this? Are they independent or dependent? Dependent, right? How about this? Independent, dependent. Dependent. Because this one, 0, 0. I says, okay, 0 times whatever, x, 0, 0, right? Right? This is a concept in independent, we understand that, right? When you m vectors, right? This is one way you can represent. Another way I can represent is also, can I represent V1, now V2, Vn? You can say this is A, right? This is another way to view matrix, right? When I say this were independent, right? It means, let's say this is X, become 0, right? If these are independent, only solution for this is when X is 0. Can you understand that? There we defined, okay, whatever linear combination, right? Combine them, then solution has, let's say, this is definition for the independence, right? So we can represent this another form, right? Also, can you represent this in these matrix forms? This is almost like, oh, this is another view. I say it's C1, Gn, right? The same, right? It's 0, right? So this solution is satisfied only if all C's are 0. Then I say this is independent, right? Because we are saying the same thing using different notations. Okay? Okay, today we reviewed about column space A. Okay? Column space A is, we see all these vectors, then all of the space span from these columns, right? Also, what is NA? It's null space. 김원중, what is null space? I think we have to review and review again, right? Then column space CA is what I say, okay, this is all of the value of X. We just transform whatever using A as a function or matrix, right? Then, okay, this is range. Whatever maps, I just mapped this subspace. This column space, right? All of the partial values of B. What's the partial values of B? This is a column space, right? Sometimes it occupies whole space. Sometimes only small subspace, right? We call column space. Then what is null space? What is null space? Kim-sang, what is null space? Eh? Null space is basic collection of all X which is satisfied X equals 0, right? So it means in this case, this is, let's say, this is point 0 vector. Whatever somehow set everything there, just map to this 0. The space here, this is a null space. Okay? Whatever value you map here, they always map to this 0 vector. That's a null space. Okay? Then I say, oh, this is A, this is X equal 0. What's the possible values for this? This is null space, right? That's definition, right? Right? If these vectors are independent, only null space is 0 vectors. These are dependent, then we have some non-zero vectors are in null space. Okay? That's the concept. Okay, so now, so we understand what are independence, right? What's the independence of vectors? Also, we understand what's the independence of column vectors, what it means. Okay, now I'll discuss about the basis. Have you heard this term basis? Let's say this is R2. Just without further consideration, what's the basis here? This R2 is a vector space, right? This space, right? Any point here can be represented as a combination of other vectors. Let's say this is V1, this is V2, then point this one can be combined as C V1 plus D V2. So I can find C and V which satisfy, let's say it is B. Okay? So this case I say is the basis. Okay? But so these are independent. Also should be minimum number of vectors. Or I may say, oh, I can do further. I'd like to introduce one more item here, V3. There's no problem. So I say, okay. I can do this way, right? Just introduce one more vectors, right? But this three-dimensional, this is most redundant. For two-dimensional, I can have only two, right? Hyung-tae, can you understand it? This is redundant, right? This one can be represented. So any point in this space can be represented of a linear combination for only two vectors, right? Right? With only one vectors? No. Three vectors? Yes. But too many is redundant. So two is enough. Okay? So basis is basically they are independent. Also, they span the vector space, but should be a minimum. When you have too many, it's just waste of money. So in this vector, I can say, okay, this V1, V2 is a basis. How about the V1 and V3? Are they basis or not of this space? Yes, right? How about the V1 and 2V1? Why? When you combine them, only point we can make is this line. Right? That's why. So the concept is actually pretty simple, right? So I don't want to do this. You can find all these spaces, not the problem. So when you try to find these bases, each vector there should be independent, okay? Also, whatever how many number of bases, it depends on how many independent vectors. So basis is not unique. So when you have a number of bases, this is minimum, right? So we call them as a dimension. Definition, dimension. Okay, so in this case, dimension 2. Okay, but when you say, let's say, three-dimensional space here, right? Dimensional space here, let's say, I may say, oh, I'm the line here. This is a line. What's the number of dimension for this line? 1, right? The dimension is 1, right? So when you have space here, then dimension is 2, right? Then let me ask another question, okay? My line is actually passed this way. It doesn't pass origin point. How about that? Hyungtak. This is just a line, but which does not pass the origin point. First of all, this one is not subspace. Why? Eh? I say the line has to pass origin point, otherwise it's not subspace. Why? 왜냐면 이게 이제 just C, right? Whatever, basically CI times VI, right? Right? If we say all CIs are 0, right? Then it has to be 0 vector, right? Because we have to allow all C's are 0, right? So that's why this origin point has to be included in subspace. Unless you include the origin point, it couldn't be a subspace. Okay, this special combinations when you just multiply by 0, then add them. Okay. So this is called dimension. So concept itself is not that difficult, just simple. Okay, this is an example. It's 1, 1, 1, 2, 1, 2, 2. So we have a matrix which is A 3 times 4, right? So column space is, let's say, CA. Okay, we try to find out what dimensions. Then we need to find out basis. Once we understand basis, then we know what the column space, right? Because all combination of bases are this space, right? So when you have this matrix, what's the dimension? Do you have any idea? What's the dimension of this matrix? What's the number of independent column vectors? Can you explain why? It is same, right? So this one we can remove that, right? We can add them, that this becomes this, right? So between two, there is no way to, so basically this is dimension 2, right? Okay? So you don't have to compute, right? Obviously when you just try whatever echelon forms, then you will find out what's the number of free columns, number of pivot columns, right? So obviously in this case, these are not those are dependent, right? These only two are independent, right? You can see, oh, I can see this is two bases, right? Okay? Another one is now from here, then they say this is dimension, here is dimension is 2. Okay. Also this matrix A is rank is 2, right? Then this null space. What's the dimension of null space? Also in this case, we have m minus r. Okay? So now we can compute the basis of m minus r. How? When we try to solve A, we solve AS equals 0, right? So we know how to compute that, right? Then from here, we found whatever this special solution, then we just linear combine them, right? Okay? So this one is basis of null space. Okay? 오케이, 잠깐만 한국말로 할게요. 지금까지 주로 개념만 얘기했거든? 개념은 사실 몇 개 얘기한 게 별로 없어요. 걔는 뭐뭐 얘기했어? 벡터가 어떻게 독립적이냐 얘기했지, 그죠? 벡터가 어떻게 독립적이냐 얘기했고, 벡터를 매트릭스 폼으로 갖고 와서 매트릭스의 칼럼 벡터란 걸 칼럼 벡터가 어떻게 독립적이냐 이런 얘기를 했잖아요, 그죠? 예, 거기서 독립적인 얘기를 했고, 칼럼 스페이스가 이루어지면 거기서 그럼 독립적이면은 칼럼 스페이스를 만들어 놓고 칼럼 스페이스의 디멘전에 따라서 베이시스 벡터를 구해야 된다 이게. 칼럼 벡터가 5개일지라도 독립적인 게 2개뿐이 없으면은 그 칼럼 스페이스는 베이시스는 2개라고. 예? 그걸 어떻게 구해야 하는 방법을 고민했잖아요, 그죠? 그다음에 이제 널 스페이스 AX 이퀄 0. 어떤 이제 소위 솔루션을 구하면서 여기서 그러면 그의 스페이스가 디멘전이 어떻지? 디멘전은 넘버 오브 프리 베리어블이고 디멘전의 베이시스는 스페셜 솔루션. 그게 베이시스다. 그게 기본 개념이에요, 사실은요. 그래서 그걸 갖고 구성을 할 수 있다. Yes. 스팬이 영어로 우리말로 동의어서 뭐 같아요? 스팬을 한다는 게. 스팬. 제가 설명을 일부 안 했는데 펜이 전부 뭐냐? 영어로 하면 make, form, 예? 우리말로 하면 형성한다? Let's say you have vector v1 and v2. Okay? So I can combine whatever this combination. Okay? When you combine them, this will represent certain collection of space. Okay? Whatever space, all of the point, whenever all the combination of C and D. In that case, I say these two vectors, I say spanning this space. Okay? So all of the point over here in this space can be represented by a linear combination of two vectors. Okay? So when I say this 1, 0, 0, 1, was a space which are spanned by two vectors. This whole space, right? Let's say now it's three-dimensional, right? This one is with three-dimensional. I say this G is always 0, right? This one plane with G is 0, right? So that's what we are calling spanning. Okay? Any other question? Let me make a 10-minute break. So I'm going to discuss about 4 fundamental subspaces. In a way, part of a lecture here is again some repetition. Up to now, we defined and learned about column space and null space. Okay? So column space, right? The column space is formed by column vectors, right? We can say this spanned by column vectors, right? So column vectors this is, I will throw away this. Like a 4 matrix, m times n. Basically, here is n and m, right? So column vectors, so each column vector here, right? So when you combine them linearly, they will form column space. So dimension is CA. It's in Rm. Jiyoung, you understand why we are m, right? This m element is each vector, right? So this is column space, right? If vectors are independent, the whole space. Otherwise, it is only subspace, right? So there's a column space, we learned about it. Then null space. Null space we defined. Now here is more X, then define B. Let's say whatever this subset of these things always map to 0 vector. So this is null space, right? So null space is NA is somehow this is in Rn, right? So n plus n because it's all x is vector x is n dimensional, right? This Rn. So up to now, actually, we learned how to compute. Let's say each area, you compute what's the dimension of a column A space or null space. Also, we learned how to compute the basis of column space and null space. Okay? So this one we already discussed how to compute this. Okay? So dimension is column space. is number of independent vectors, which is also called, we can say, rank of the matrix. Okay? So rank of the matrix, this one is rank of the matrix is R. Then, oh, this one is null space. Oh, sorry. Okay. CA. What's the dimension of this null space? Is M minus R. Okay? Because all x's are actually n, right? Because we always say a m times n with x should be n, right? Then this one is bm, right? That's why. Okay? All these possible b values, this is columns, and yeah, this is, that's the way we can compute this null space and column space. Actually, row space, left null space, just almost identical, but only definition is just transpose. Just take A, then transpose. Actually, when you transpose, it's basically when you have A, then we say, okay, this is the A. I say, okay, this is column vector C or whatever. We just say this V1 to I call Vn, right? Okay. When I say A transpose, when you transpose, now this one is m times n. Transpose is now it's n times m, right? When transpose, right? Then this one is backtracked somehow. You say this is V1, right? Now actually transpose, you can say, oh, it might be also okay, this transpose. So column vectors of AT, in a way, is row vectors of A, right? So actually, we didn't define row vectors, but column vector. Similarly, we can define row vectors. Row vectors is from original vector. This is row 1, row 2, row 3, whatever this row m, this m vectors, right? So row space is somehow, okay, by linear combining these row vectors, now we can make row space. It's almost the same concept. Okay? So you can say this is column space A, then row space of A. A is actually column space of A transpose. Okay? It's concept simple. Then what's the dimension of this column space of AT? We define rank, right? Rank of A. What's the definition of rank of A? Number of pivot variables, right? So rank of A is also rank of AT transpose. So number of independent column vectors is the same as number of independent row vectors. So rank are same. Okay? So then dimension, I say dimension of A, here is R, rank. Also dimension of this is also R. Okay? Then we just also left null space is almost equivalent to null space of A transpose. So we have actually 4 different concepts. Depending on the cases, we may use all of these. Sometimes we use some of them. So just try to familiarize these 2 concepts. These are only applicable just this is case of transpose. Okay? Then I'll show some very interesting diagram. This is space of Rn. Okay? So row space is actually, this is one row, right? How many elements here? It's n element, right? That belong to Rn. Okay? Rn, right? This rank is R. It means here independent row vectors are 2. I don't know R. The number of independent row vectors, or I says basis of row space, its dimension is R. Okay? The remainder belong to null space. Okay, so in the column space, and this is equivalent. Okay. Do you have any idea why I draw this specifically very strange form? We don't know yet, right? Actually, that's the one I'm going to discuss next week. The orthogonality, the 2 spaces are orthogonal, but today I'm going to skip them, okay? So I'm going to introduce them next week. Okay, so I introduced 4 concepts, different subspaces. Oish. What's this? This is A/U, and A just go to /U, then go to R. What's this? 김상우. This is echelon, right? Echelon form, right? This row reduced echelon form, right? So we just transform from original matrix to move this way. From here, we find the pivot fully, right? Then we just go further, try to make whatever pivot variable is 1, right? Then others, whatever form is, whatever IF or 0, 0, that kind of forms, right? So that's a space. Let's discuss about a column space. Just use this one here. So we try to find out what's for each subspace, try to find the basis and dimension. Column space, right? So I don't know, I already talked about column about more than 10 times now, right? Is column, is space, is just think about it as a range of a function. Like in the case of y equal fx, what's the possible values of y? There's a range, right? So that's actually this column space. So basis vector from pivot columns of A, the rank is R number of pivot. So basis column vector CA. Then from there, I can say, okay, when you transform A to L, U, right? U. From U, this one is a pivot pair of columns. I say this one is free. Okay? There's a transformation you did, right? So pivot means this is non-zero, right? On the pivot, right? So in that case, what's the basis of this U? Then we have CU, this column space of U. What's the basis vectors for this? These two vectors, right? These are free, just you can ignore them, right? Then in that case, what's the CA? CA is actually you had original, whatever. You had 5 of them, right? You go through this elimination. You found first one, third one is pivot. So here's, I can see it. First one, third one. I can say this is a basis vector of column space of A. Okay? This is basis vector of column space of U. Okay? So dimension is in this case number of columns 2. Okay? That's the way you do. So column space of A is different from column space of U. Okay? The null space, you know how to compute this. Dimension is n minus r. Then basis is we need to find out special solutions. Okay. So how many special solutions? Let's say n minus r. For example, in this case, there's 3 free variables, right? Then in this case, dimension of null space is 3. The special solution has 3 special solutions that we have to combine them linearly. So each of the vector, there is a basis of this null space. Now let's discuss about row space. So initial matrix was, let's say, 1, 2, 3, 1, 1, 1, 2, 1, 1, 2, 3, 1. Are these vectors independent or not? I say row vectors. This is the first row vector, right? This is the second row vector. This is the third row vector, right? This is identical, right? So it means this is identical. You can remove them. So only 2 independent row vectors, right? So here is rank is 2. Okay? So what's row space? Row space is, let's say, row space AT in R4, but rank is 2. No. 2, then n minus r is number of free variables are 2 as well. Then that's the way we can define, okay, so r is 2, then these 2 bases here, okay, then say rank dimension is 2. Okay. Here's another one is actually from here actually I from A we just go through reduction. Then this is U, right? Then we go further. This is R, low reduced echelon form. Okay? So in this one actually, oh, this also, so A and R. Here what I'm saying is, when you convert A goes to U, go to R, column space of A may not be as column space of U, may not be a column space of R. Okay? But this row space, right? Same when you have so when you have a linear whatever this row operation, actually doesn't change. So in this case, A basis vector is 1, 2, 3, 1. 1, 1, 2, 1 is also basis vector. Also indicate same basis spaces. Do they form same subspace or not? Their bases are different, right? But still same space. Because when you have one space, you can choose any set of independent vectors. Doesn't have to be unique. Like when you're two dimension, I can have V1 and V2. That's the one way I can find the basis vector. Another one is, no, I don't want to do that. I say this. Oh, shit. I can say U1 and U2 is another set of basis vector, right? Even though bases are different, they span the same space. Okay? So this is the basic concept. I'm going to skip this left null space. Probably just except I'm saying just that there's a just null space of A transpose. Okay? Any questions on today's lecture? 자, 강의 10 끝내고요. 한국말로 질문 받을게요. 혹시 뭐 질문 있어요?